Alrighty, let's go ahead and get started. So it's been a while since the last class with Mardi Gras and all of that. So I'll go ahead and kind of review what we've been doing in the previous classes. And also let you know what to expect in the coming days. So today we plan on finishing up our discussion about circuits, work some examples, make sure we understand the topic. And then Thursday, we'll have an exam review, talk about what to expect for this first test, what topics will be there, what the formatting will be, and all of that kind of stuff. And then next Tuesday, we'll have our first test. So that's kind of the plan. Today, finish circuits. Thursday, exam review. And Tuesday, the 15th, be our first test. All right, so with circuits, what we've seen so far is firstly, the big equation is called Ohm's law. And it relates the voltage supplied by the circuit. And the voltage you can think of kind of like the ability for the circuit to pump the electrons through the wires, kind of a thing, is equal to the product of the current. Capital I is the current, and that is how many electrons are flowing through the wire per second is a way of thinking about that, times the resistance of the circuit, R, where the resistance comes from whatever elements or devices or things like that you place into the circuit. It could be light bulbs, TV, toaster, coils of wire, things like this are all examples of what can be considered resistors. And so with Ohm's law, you can answer questions like, here's the circuit with this set of resistors in it, calculate the current which may flow through this circuit. Another equation is for the power. So this particular equation comes in basically three different forms, depending on what it is you know about the circuit. The form I always remember is that the power is equal to the current times the voltage. Okay, so if you know the total current which flows through the circuit, and you know the voltage supplied by the circuit, you multiply them, you get the power. And then, of course, you could use Ohm's law, apply it to this power equation to see what the other two versions of this equation are. And another one is power is equal to I squared times R. And I get this just by replacing the V in power with V equals IR. So now you have I times R, which is I squared times R. And so you would use that version if you don't know what the voltage is, but you do know what the resistance is. And of course, the last one, the power, is V squared over R. And this one, again, I use Ohm's law. I solve it for the current, I. And then I replace the current in my power equation, and it becomes V over R squared, basically. Now, any one of these can be used, depends what you know. Generally, for the types of questions we're going to have in this class, the first one is what you're going to have. You're going to know what the voltage is. You have the battery sitting there or the voltage source, whatever it is. And likely, the first part of your question is going to be to calculate the total current. So you know the current, you know the voltage, multiply them, that gives you the power. But these other two exist as well. That way, so if you are, studying from a different source, you're looking on YouTube, you're looking in a textbook, and you see one of these other versions, just know that's where it came from. I remember P is I times V, and then I can get the other ones if I need them. So those are the two main fundamental equations when doing our circuit analysis. However, the details involved get a little bit more complicated by the fact that the general circuit you will be given to analyze will be kind of complicated. It's not going to be just one resistor sitting there, and so I times R is easy to calculate. Rather, you're going to be given circuits with multiple resistors, and those resistors can be connected in various different ways. And so the next topic that we discussed was, how do you combine resistors together to get down to some final simplified version of the circuit with only one resistor in it? That way you could use Ohm's law. And what we found was resistors can be connected in either, for our purposes, in either series. So if we have resistors in series, then the total resistance of the set of resistors that are connected in series, total resistance, is just given by the sum of each resistor, R1 plus R2 plus R3, and so on. So you have a circuit, some set of resistors are connected. Some of them may be in series. Those that are in series, you can combine them together in this way. Okay, and so what series may look like is something like this. Okay, that's something like a series connection. All three of these resistors are connected in series. How do you know whether it's series or not? Well, the best way, there's a variety of ways. One of the best ways is to imagine what the electrons are doing as they flow through the wire. Resistors are connected in series if the electrons go from one resistor to the next without some option of skipping it. So in other words, when the electrons leave the voltage source and they hit this first resistor R1 here, they all hit R1. None of them miss it. Okay, fine. Then when they leave R1, every single one of those resistors then has to hit R2. There's no other path for those electrons to take. And since any electron that hits R1 must also then hit R2 and cannot be avoided, they must be connected in series. And same, of course, for R3 over here on the right. Just because it's over there on the right side, it's still just a wire connecting these resistors. And so the electrons go from one to the next with no option of avoiding the resistor. They can't go to another branch or another path. So they're connected in series. If they're connected in series, you just add the resistances together to get a total resistance. Now, the other way we're going to deal with, or we've been dealing with, I should say, is resistors in parallel. This, of course, is the slightly more complicated version. And what this says is if you have some set of resistors that are connected in parallel, and we'll see what that means, the total resistance of that set, 1 over that number, so 1 over the total resistance, is given by 1 over R1 plus 1 over R2, and so on. Okay, so this one's a little bit funky. Instead of just adding the resistors, you have to add the reciprocals. Okay, but not only do you add the reciprocals, and this is the key thing here, this is where a lot of people make a mistake, especially when they're rushing to get through the test. Not only do you add the reciprocals, but once you've done that, you then have to take the reciprocal of that answer, because what the equation says is 1 divided by the total resistance is given by this thing, not the total resistance itself. So if you're adding these things together and you get an answer of 3/5, well, then you have to flip it and make it 5/3. 5/3 would be the answer. Okay. Now, how do you know if resistors are connected in parallel? Well, here's an example. Okay, these two resistors are connected in parallel. How do I know? Well, again, try to visualize what the electrons are doing. As an electron leaves the voltage source, it reaches this point right here. And at that point, it now has a choice. It can either go to R1. If it does it, it leaves R1, comes here, and then just goes along its way all the way back to the beginning of the circuit, never touching R2. Or the other option is the electron, when it reaches that first node, can go upwards instead, and it can hit R2. It then goes through R2, continues along, and just continues back to the beginning of the circuit, not touching R1. And so in this case, the way these resistors happen to be connected, an electron will either go to R1 or it'll go to R2. But no electron in this circuit will ever hit R1 and R2, one right after the other. If it goes to R1, it has to skip R2. And if it goes to R2, it has to skip R1. And so that's the big difference here between series and parallel. Series, the electron has no choice. If it goes through R1, it must go through R2 afterwards. There's no other way for it to go. So those are series. Here, if an electron goes to R1, it inevitably skips R2. And vice versa. If the electron hits R2, it has to skip R1. Thus, those are in parallel. And then, of course, we have combinations, and which is what a realistic circuit analysis problem will have. You're not just going to have one of these examples, but likely you're going to have an example where both exist at the same time. So you may have something that looks like this. And now in this case, what's going on? Well, I think it's fairly visually intuitive to see this and say, okay, it looks like R2 and R3 are parallel. And then if we combine those together, R1 will be in series with that thing. But let's make sure that's true. Can't I say R1 and R2 are in series? They look like they would be in series. If we just forget about R3 for a second, then this would be exactly the same as the top example. However, think about the electron. What's going to happen? Electron hits R1. It then reaches this point. At that point, the electron can have an option. It can either go up to R3 or go through R2. So every electron that hits R1 will either hit R2 or R3. However, what's important is no electron is forced to go from R1 to R2. I can't say, if you give me a random electron and you say, okay, where's it going to go? I don't know. So I can't say R1 and R2 are in series because I can't tell you for sure that if an electron goes through R1, it will definitely go through R2 because maybe it goes through R3 instead. And of course, the same holds the other way. I can't say R1 and R3 are in series because maybe after it hits R1, the electron hits R2 instead and misses R3. So at the beginning of the problem, R1 is not in series with anything. So I leave it alone and I'll work on what I can work on. And in this case, what I can work on is the parallel thing. I know for sure R2 and R3 are parallel because every electron that hits that node will either go to R2 or R3. but no electron will ever hit R2 and R3. It must choose a path. So they're in parallel. So what I would do is I would combine R2 and R3 in parallel using the equation. And then this circuit will now become some new circuit, which is equivalent. It's called an equivalent circuit. It just means it works the same way, but looks easier. This R1 hasn't changed. It's still sitting there. But now that parallel set of R2 and R3 is now transformed into a single resistor sitting there, which I'll call the R parallel thing. This is still R1 from the beginning. And now I see, aha, R1 is in series with something, but the thing it's in series with is not R2 and it's not R3, but rather it's this R parallel, this combination of the two that I had to solve for. How do I know it's in series? Well, if an electron hits R1, it must go through R parallel afterwards. It has no choice. There's nowhere else for it to go. So they're in series. And so this is going to be the key to solving problems. You're given a complicated circuit. I say complicated, but they're not truly complicated. They're just not the simplest circuits I can possibly give. Some complex form of a circuit which has resistors connected in all sorts of ways. And your job will be to take this complex circuit, whittle it down little by little, combining resistors when you can see if they're in series or see when they're in parallel, to simpler and simpler forms of circuits, until at the end of the day, you're left with one single resistor whose total resistance you've been calculating this whole time. Once you've been able to do that, you use Ohm's law and the power equation to solve for whatever the question may be asking. And the key, the kind of art of this analysis is, yes, we know the rules and we know the equations, but it's not always perfectly clear. You always do this or you always do that. You have to look at your particular circuit and see what you can do first. As I said, I can't mess with R1 at the beginning of this example. So I have to move on to something else. And in this case, the other thing I can move on to is R2 and R3. Other examples, maybe I have to do the series thing first. And once I've done the series thing first, then I could start working on the parallel aspect. For instance, an example of that is this. Let's say I have this example. Here, I have 3 resistors, just like before, but now I say, okay, there's definitely some parallel stuff going on here, right? R3 is definitely parallel to R1 and R2 in some way. However, is R3 parallel to R1? The answer is no. Is R3 parallel to R2? The answer is no. What R3 is parallel to is the combination of R1 and R2 combined together. Okay, so when I get this circuit, I can't say, combine R3 and R1 in parallel, because they're not. R3 is parallel to this other branch, and that branch has multiple things. So combine the multiple things together first. So I would look at it, I'd say the bottom branch has R1 and R2. And if I'm thinking about an electron, when an electron hits this node, it has an option. It could go up to R3, fine. If it does that, it skips over R1 and R2. Or if it goes to the bottom branch, what would happen? Well, it would hit R1 and then have to hit R2. Once it hits R1, there's no choice but to hit R2. So I know R1 and R2 must be series. So I would connect R1 and R2 in series first, combine them together. When I do that, I would have a new circuit where that bottom branch I've combined into one single resistor, which I'll call R series. And the top branch is still sitting there because I haven't messed with it yet. That's still R3. And now I see what's in parallel. Now I can say R3 is in parallel with RS, our series. It wasn't in parallel with any of the individual R1 or R2, but it's in parallel with the combined thing. And so this is an example where I do the series part first, and then I do the parallel part. So I hope this shows that there's not one right way. I can't give you a recipe and say for every single circuit, follow these steps, because every circuit is different. Sometimes you have to do this part first, sometimes you have to do that part first. And there's no way to tell until you look at the circuit what you have to do. And even then, especially when you're doing really complicated circuits, more complicated than we'll get in this course, you may be going down a path, working it a certain way, you think it's going fine, and then all of a sudden you get stuck. You say, oh, I must have started with the wrong thing. So you have to start all over and work on something else first. And maybe that path will get you to the end. Okay, so there's a lot of art, there's creativity in this, circuit analysis stuff, instead of it being just a straightforward, boring, crank it out like a machine, here are the steps of the recipe. You know the equations, you know the rules. The rest is you look at the circuit and try to think your way through it. Which things should I combine first? Once those are combined, what's the next thing I can combine? And just go one step at a time until everything's combined at the end of the day, and then you finish the problem. All right, so before I work some examples, are there any questions about this? All right, so again, this was just a review. I mean, there's nothing new here. We've done this before. This is what we've already done. But since it's been a while, I wanted to make sure we kind of remember what we've been doing. Now we'll work some examples just to make sure. So let's say for each one of these examples, at the end of the day, what I want to calculate is find the total current and power. Okay, that'll be the main questions. Here's our circuit. Let's say we have this. There we go. 10 volts, 2, 6, 3. All right, so here's a circuit. It's got some set of resistors connected in some way. And at the end of the day, what I'd like to do is know how much current will flow through this circuit. And in doing so, what's the power output by this circuit? Okay. Now, when you get to more advanced courses, so when we get to general physics and we deal with circuits, we're going to add on to this. Instead of just wanting the total current of the circuit, I may ask, what's the amount of current which specifically flows through this branch only? Okay, so maybe the circuit has 4 amps of current running through it as a whole, but we know when it reaches this node here, the electrons split. Some of them go to the first branch, some go to the second. So if you started with 4 amps, you won't have all 4 go to 6, and you won't have all 4 go to 3. Some of it will go to 6 and some of it will go to 3, and you have to figure out how much, what will be the split. Okay, that's getting a little bit more in depth into this circuit analysis stuff. You start looking at specific resistors in your circuit and say, how much voltage does this resistor drop or use up? And stuff like that. For this class, however, since we're just introducing the topic, all I'll be asking you is what's the total current and the total power. So just make note of that. All right, so when I look at this circuit, I say, okay, what do I know? The electron will hit the 2, move along, and then get to this node where it will split. Because there's a split, there's an option for the electrons. So I know I can't mess with the 2 yet. Because any electron that hits the 2, I can't guarantee which way it'll go. Sometimes it goes to 6, sometimes it goes to 3. So 2 is not in series with anything yet. However, what I do know is that the 6 and the 3 are in parallel with each other. Because an electron that goes to the 6 will never hit the 3. An electron that goes to the 3 will never hit the 6. And of course, we remember the other rule that also helps is how many nodes do the resistors share? Well, the 6 and the 3 share 2 nodes, the top and the bottom node. And we know the rule is if resistors share 2 nodes in common, they're in parallel. And if they only share 1 node in common, they're in series. So the 6 and the 3 are in parallel. So let me go ahead and combine them. So I'd say first, 1 over R parallel is 1 over 6 plus 1 over 3. Now, of course, you will have a calculator, hopefully, when you're taking this test. So you just plug it in. I don't have a calculator, so I'm just going to do the fractions. If I'm adding fractions, I have to remember the rules. And the rule is, in order to add fractions, you have to get a common denominator. In this case, the common denominator is 6. So this is the same as 1 over 6 plus 2 over 6, which is 3 over 6. And I know 3 over 6 is the same as 1/2 if I simplify it down. However, that's 1 over R parallel. So I need to flip the answer to get R parallel itself. R parallel then is just 2. And so now I know that this combination of resistors, is equal to a single resistor whose value is that number I just calculated. So now I can redraw my circuit. And now, instead of that parallel set, I have one thing sitting here. There it is. This is still 10, this is still 2, but now that parallel set has become a single resistor whose resistance is 2. Now I say, okay, I combine stuff here. I try to simplify this down. What do I have? I've got a circuit with 2 resistors. How are they connected? Well, in this case, they're connected in series because every electron that hits the first resistor must hit the second resistor. It's got no choice but to do it. So they're series. So I combine them in series. R series is equal to 2 plus 2, which is 4. So now I know the total resistance of this circuit is 4. 4 ohms if you want the units, of course. All right, so that's the first big step. In order to calculate the total current and the total power, well, first of all, the total current, obviously I want to use Ohm's law. And Ohm's law says V equals IR. So if I calculate I from this, I bring the R to the other side. This becomes I as V over R. So in order to get this number, I need the total voltage, which I happen to know that's given in a problem, 10. Okay, fine, 10. And I need the total resistance. Well, at the beginning of the problem, I don't know the total resistance. So I did all of this work simply to get the total resistance of my circuit. And what do I know? I calculated it to be 4. So 10 over 4 is 5 over 2 ohms. Or if you want the decimal is 2.5. All right, so there's my total current. Any questions so far? Calculating the resistances or anything like that? All right, the last piece, of course, is calculating the power. Well, that's easy. Once I know the total current, well, it's straightforward. Power is I times V. And I know I just calculated is 5 over 2. And V is 10. So this is 50 over 2, which is 25 watts. Oops, I'm sorry, it's not ohms. I'm solving for current. This is amps, my lord. So 25 watts. And there we go. This is how we solve, or this is a typical circuit analysis problem for this course. You're given a circuit with some number of resistors. Those resistors are connected in series and parallel, a combination of both. And what you'd be asked for is to find the total current which flows and the total power. The method, there's no one way to do it. It's up to you and it's up to the circuit itself. But you're going to look at the circuit, look at its resistors, and see what sets can you start working on immediately. And in this case, I can't work on the 2 yet because it's not in series or parallel with anything. However, the 6 and the 3 I can work on because they are parallel to each other. So I work on them first. I combine them in parallel, get an answer, and then I replace that set with an equivalent resistor whose resistance is whatever I just calculated. And now I look at the new circuit. I'll say, now what can I work on? Well, now that original 2 is in series with something. It's in series with this thing I just calculated. So I combine them in series and I get a total resistance. Now I know the total resistance. I use Ohm's law. I use the total voltage of the circuit, the total resistance of the circuit. That gives me the total current. I have the total current. I want the power. I just multiply it by the voltage, and that gives me the power. Let's try another example. Again, same question, find the total current and total power. So let's say we have there we go. Let's say this is 2, this is 6, this is 4, 2, and 3. All right. So here I have a circuit, certainly complicated looking, a whole bunch of resistors all over the place, and I want to try to calculate the total current. In order to calculate the total current, I need the total resistance. So what do I know? Well, I start at the voltage source and I say, okay, what happens to the electrons? Well, they leave, they come up here to the 6, and then from there they keep on going, and then they hit this node where there's a branch. There's separate paths. So the 6 I can't mess with yet, because if it hits the 6, I don't know where it's going to go afterwards. It's not guaranteed to hit either the 3 or the 4 or the 2. So I leave the 6 alone for now. And I say, okay, well, what about this thing that kind of looks like it's parallelish? Right? I've got the 4 and the 2 on one branch, and I've got the 3 on another branch. So those 2 branches look like they're parallel to each other. However, I can't mess with the parallel set until I first take care of the fact that this 4 and the 2 are in series on this one branch. In order for me to calculate the parallel aspect, each branch can only have one resistor on it. If it's got multiple resistors, I have to combine them first. So here, the 3 is by itself on a branch, but the other branch has a 4 and a 2. So combine those together to get one resistor first. And I know those 2 resistors are in series because any electron that hits the 4 will inevitably have to go through the 2 right after. All right, so we start with series, our series. is 4 plus 2, which is 6. Done. Now what do I have? I redraw it. Here's the 6 there. Here's this first branch. Here's the second branch. Right, 2, 10, 6, 3. So all of those are the same. And now all I've done is connected the 4 and the 2 in series to create one single resistor whose resistance is 6. Now what do I do? Well, same thing. Electrons hit the 6, keep on going, reach this node here where the path branches off. Now I see the 6 and the 3, those two are in parallel with each other. So what I want to do is combine these two together in parallel. Now, don't make the mistake of trying to add in this other 6 because it kind of looks like it's also parallel, right? They're all vertical resistors. That 6 on the left is not parallel with the other 2. Okay, and one way of seeing it is, what are its nodes? Well, it's got a node here, and it's got a node here. Well, the top node is the same as the top node for the 6 and the 3. That's good. However, its bottom node is not the same because that voltage source is in the way. And the 2 ohm resistor is also in the way. So that 6 on the left only shares one node in common right now. So it can't be in parallel with the other 2. So again, I leave the 6 alone, it's on the left, and I only mess with the set that is in parallel, which is the 2 on the right. So I say, okay, parallel, 1 over R parallel is 1 over 6 plus 1 over 3, which is 1/2. However, again, I have to flip it to get the actual answer. R parallel is 2. And now I can redraw it. Say, what do we have now that I've simplified it a little bit? Well, this 6 over here is still the same. That hasn't changed. Now, this 6 and 3 on the right that were parallel to each other has become one resistor. Here it is. And his resistance is this value I just calculated, which is 2. Then I continue on. This resistor at the bottom is still the same, the 2 and the 6 on the left. Okay. Now what do I have? Look at the electrons. The electron hits this 6, keeps on going, and then has to hit this 2. There's no choice. So I know this 6 is series with this 2, but let's keep on going. The electron that hits the 2 keeps going and then hits this other resistor with no choice but to hit it. And then after it hits that, it goes back to the beginning. So every electron that hits the 6 will also hit the 2 and the other 2. So all 3 of these resistors are series with each other. So I can combine them in series. Our series is 6 plus 2 plus 2, which is 10. So what am I left with? I'm left with a single circuit with only one resistor sitting here. Let's put it there. And his resistance is whatever I just calculated it to be, which happens to be 10. Once I've gotten down to this point, I'm done. I now know the total resistance of my circuit is 10 ohms. However, the problem is not asking for the total resistance. What it's asking me for is the total current. So V equals IR. I use that to say I is V over R. The voltage of my circuit is 10 volts. The resistance, I just calculated it to be 10. So I have a total current of 1 amp. Last question, what's the power? Well, power is just I times V. I just calculated is 1, and the voltage of my circuit is 10. So I have a power of 10 watts. And now we've done it. We've taken the complicated circuit with 5 resistors in it, with some combination of series and parallel all over the place. And I say, given this circuit, what's the current that would flow? Well, I little by little combine resistors together when I see if they're series or parallel, until at the end of the day, I'm left with a circuit that only has 1 resistor in it. So I now know the total resistance. Once I'm at that point, now I can use Ohm's law. I is V over R gives me the total current. P is I times V gives me the power. All right, so any questions about that? Well, that's pretty much it. That's what you can expect from questions on the test or the homework or things like that for this topic. You're given a circuit, you have to combine the resistors and then calculate the current and the power. So if you could do these examples, obviously the test questions will be different. You know, how the resistors are arranged will be different, but it'll still be the same basic principle. Some are in series, some are in parallel. I can't say for sure which one you should do first. In this case, you had to do the series set, and that allowed you to do the parallel. And then once that was done, everything now is in series. Previous example, what did we do? We had to start with the parallel set first. Once we did the parallel set, now that thing is in series, and I combine them in series, and now I have the total resistance there. So each problem will be slightly different. What is connecting them all together are the rules. If they're in series, you combine them this way. If they're in parallel, you combine them this way. Once combined, move to the next step. Now what can you do? Down to the end. Once you're at the end, you use Ohm's law and power to get whatever answers it is you're looking for. So that's it. We are now done with all the topics that are going to be on this first exam. Next class, of course, we'll do an exam review, but just so you know, and I'll repeat this next class, what to expect from the test. For anyone that didn't have me for first semester physics and you're not sure what my tests look like, first of all, the test will be online. And the way it'll work is, rather than setting it on Canvas as a timed test where you have to go onto the website and you answer the questions on the website and you have a 50-minute timer or whatever, I'll be doing it in the form that I do the homework problems. I'll upload a PDF to Canvas in the morning of Tuesday. You would download it, work out the problems. You could either work it out on the test itself or blank sheets of paper, whatever's more comfortable for you. Work it all out. You'll have some period of time. Likely, I'll give you till the end of the day, the midnight that day, to submit it back, just like you submit the homework. So you'd either scan in the thing or you take pictures or whatever and submit it back to Canvas. So that's going to be what you can expect. If you've, and obviously you have, if you've done the homework problems, then you know exactly the process to do the test. Same exact thing, only now it's more formal, being a test rather than homework. And again, next class, I'll do the test review. What I'm going to do is go over all the topics that we've covered thus far, just to remind us what we've done, kind of go over what equations there were and things like that, and then give you an opportunity, the last opportunity, of course, to ask me questions on the topics. If there's a particular problem you're having trouble with, or an example you want me to work out, or anything like that, that'll be your opportunity. So for sure, what you want to do is take some time before Thursday to look through the material, what homework's been assigned, what practice problems are on Canvas, and go through them and see, okay, what am I having trouble with? For whatever reason, I'm having trouble with the parallel resistors, or I'm having trouble calculating the total electric force, or whatever it is. And then on Thursday, you ask me a question, a specific question for that. And that way, instead of me working out examples that no one needs an example of, I can work an example that's important to you. That'll help you with what you're having trouble with. Once that's done, of course, whenever the exam review is done, you're done for the day. And Tuesday of next week will be the test. Of course, we won't be meeting for class on that Tuesday since you're going to be working the test. But we will then be back the following class period Thursday to start on the next set of topics. So, any questions for me? All right, well, in that case, you're free to go. I sent an email regarding the LAMP meeting going on today. They're on campus. It's in PSB 164. I certainly recommend everybody goes and attends because they're going to talk about various things, including, I know the research symposium going on this semester, but also, what kind of things are available to you, whether it's tutoring, free tutoring, or MCAT prep, or all sorts of different things the LAMP program offers to members of the LAMP program. And so you definitely want to go figure out, if you're not a member yet, they'll let you know how to sign up, what application you need to fill out, and all of that stuff. So definitely go see what's available, because there's a lot of stuff students don't realize are available to them that they should be able to take advantage of. So other than that, I'm done. So you're free to go, and I will see you on Thursday.
Thank you.
All right, see you later.